Welcome students to my series on mechanics. We are taking this first lecture on fundamental of dynamics for the students of B.Sc Honours Physics of University of Delhi. Already from your earlier classes you have a basic idea about the dynamics. Let's start this with some of the basic terms which we are going to use in this chapter. Let's quickly revise these terms. Let's start with the term dynamics. Dynamics is a branch of mechanics in which we talk about the position, velocity, acceleration of the particle at any instant of time in light of its cause. Primarily it is an unbalanced force which makes the body to change its position or change its velocity, or maybe a situation is like this, that there is no unbalanced force. The body maintains its velocity throughout the motion, that is the uniform motion, as a special case of dynamics. But we do care for the cause when we talk about the dynamics. There are three important physical quantities with which we are dealing. One is position, normally represented as r vector. Velocity or instantaneous velocity represented by v is time rate of change of position. Acceleration, a vector, which is nothing but is the time rate of change of velocity. The variation of these three with time, in a nutshell, is what we discuss in dynamics. Obviously, we talk about force, we talk about linear momentum, we talk about impulse, and so on and so on. There is another term which we are going to use quite often in the discussion, and that is particle. This is a hypothetical concept. Obviously, any three-dimensional body, how small it may be, it is having some dimension. That means it starts from some position and ends at some other position, and there is small difference between the two. For example, I have an object, real object. Say this is my x-axis, this is y-axis. I can say my body extends from value x1 to x2 along x-axis, and from y1 to y2 along y-axis. It means in order to define the position, I have to give x1 as well as x2. Same I have to do y1 and y2. This makes the mathematics very complicated. Instead, what we do is we represent whole of this object with one point P and say, yes, this is the particle that is representing this object. And the advantage we are getting is, this particle has a specific position coordinate along x as well as along y axis. Though this is the simplification we have made with small, say, relaxation, but it becomes mathematical convenience later on because my position is well defined. And in order to give the position vector, as we had discussed, as a parameter, I can represent it by one single vector starting from the origin of the coordinate system and terminating at this point, which I can't do for this object. There may be many vectors I have to define in order to give exact geometry of this object in my coordinate system. This particle is supposed to possess the same mass as the mass of the object, supposed to experience the total force experienced by this object, and possesses the same linear momentum as that of the object. Next thing is to discuss regarding the concept of rest and motion. When can I say the body is in rest position and when the body is in motion? One simple definition is that if my particle or coordinates of the particle rather, they are not changing with time, I say yes, the particle is in rest position. And if they are changing with time, then obviously I say the particle is in motion. But here there is one problem to understand. This is an object. Obviously I am representing it as a object. This is a real object, but this is what the simplification, as we have discussed, will take. There are two observers, O1 and O2. Now if you ask from this observer, give me the position of this object or the particle, he will give this distance from him. Let's say this is 5 meters. But if you ask this observer to give the position of this particle, he will give this distance and say, for example, it's 2 meters. It means in order to give the position to this particle, I have value 5 meters from this observer and 2 meters from this observer, which makes very clear that position is not an absolute quantity. It is always changes when we change the observer or the observation points. In order to give position, it is important or rather necessary to define the observer. I can take the observer anywhere. It's mathematical permission we have while discussing in dynamics. But preferably, we select a coordinate system and the observer is supposed to be present at the origin of this coordinate system. It is not a hard bound rule, but it's only a matter of convenience. When I say the frame of reference, I am actually referring to a coordinate system. Let's say this is x-axis, y-axis, z-axis, or you can choose in any of the formats, it's not very important. This is my particle P, which is supposed to have coordinate x, y, z at time t. Coordinates are x, y, z, position coordinates at the time t. What is the meaning of all this? If I drop a normal on the xy plane, then this distance is a normal point or projection point. Then this distance, which is parallel to the x-axis, will measure x, and this distance, which is parallel to y-axis, will measure y, and this distance, which measures parallel to z-axis, is z. This is a simple Cartesian coordinate system, and the meaning of the position coordinate defined in the Cartesian coordinate system. Although it is not necessary to take always the Cartesian coordinate system, you can choose the other coordinate systems like cylindrical coordinate system, spherical coordinate system, depending upon what is a type of the motion with which we are dealing with. This coordinate system is a frame of reference, which means that when I say the position is x, y, z at time t, I am always referring it to the origin of this coordinate system. That means with respect to the origin of this coordinate system. But depending upon the status of this origin, there is a classification for frame of references. Basically, there are two types. Inertial frame and non-inertial frames. Suppose I have two frames, one I call as S frame and other I call as S dash frame. This has its origin O and this has its origin O dash. If the relative velocity of these origins, which I am representing as Vf vector, that is the relative velocity, of O dash with respect to O, remains constant with time, I call these frames as inertial frames. But if this relative velocity is not constant, or rather I have relative acceleration which is non-zero, I say the frames are non-inertial frames. Primarily we are talking about the inertial frames. Of course, at the end we'll also describe the non-inertial frame. So let's focus on inertial frames presently. Let's take one example. On the roadside, I have a pole. If I fix one frame on this pole, same S frame, and there is a car going in this direction with the velocity, let me call this velocity as Vf, and there is a frame attached to this car. This is the S dash frame, this is frame, and this is constant. When I say this is constant, I mean that its magnitude and direction both remain same with time. These frames are inertial frames because their relative velocity is not changing with time as per definition. Now there is a important point to understand. Suppose there is a bird, right? There is a bird which is flying and is observed by both the frames O and O dash. I hope you understand this, that the observation made by O and O dash, they are different. Can we link the two? Can we have some relation where I can transform what I have information in S dash frame, in S frame, or vice versa? That means I am looking for a system of transformation from one inertial frame to another inertial frame. This transformation was given by Galileo and known by his name, Galilean transformation equation. I am repeating once again, when we say the Galilean transformation equation, we are only dealing with inertial frame. Here it's important to add one more thing, that this relative velocity should be very, very small as compared to the velocity of light. We'll deal with those cases where it's comparable to the velocity of light in a separate transformation equation known as the Lorentz transformation equation. But at present we are only having this condition applicable so that we get one set of the equation, which of course are very useful for our day-to-day life, because we see the object like car, aeroplane, they are moving with the velocity which is satisfying this particular condition. How to drive? For this, we have to first of all take two frames, S and S dash. For convenience, I am keeping the S frame always in rest, and only S dash frame is moving with the velocity, that is the relative velocity Vf vector. Suppose that time t equals to 0, that is the initial time. Both these frames are coinciding with each other. That means I have x, y, z, and exactly on it, though I am showing it with small difference, but it is lying on it, I have y dash, z dash, and x dash. That means O and O dash both are coinciding with each other. Then at time t, because S dash frame is in motion, they separate out, and now I have this geometry: x, y, z. This is O dash, X dash, Y dash, Z dash. This is my S dash frame and this is S frame. They get separated out because S dash frame is moving with some velocity. Since they are inertial frame, this relative velocity remains constant with time. If I join it, this vector is Vf vector into time t, because they were coinciding with each other in the beginning, and then this frame S dash has moved with the velocity Vf, and obviously will cover a displacement which is Vft. Let's take now a point P in space somewhere. Now we are supposed to give the position of this point P both with respect to O as well as with respect to O dash. In order to do this, we have to talk about the position vector. How can I do it? This is my position vector which I am taking from O, this one, this is the position vector taken from O, and let's say this is given as R vector. But the position of this point P is also defined from O dash and this position is given as R dash vector. Let me quickly repeat what I said. These two frames, S and S dash frame, they were coinciding with each other at time t equals to 0, out of which the frame S dash has moved. At time t, this frame S dash is somewhere here. Origin of S dash frame has moved a relative displacement Vft. Now at this time t, I am supposed to give the position of this point P from O as well as O dash. From O, the position vector is this one and is given as R vector. From O dash, the position of this point P is given by R dash vector. Now we have to relate this R dash and R. That will be our first Galilean transformation equation. And we can do it in a very simple manner. Using the triangle law of vector addition, I can write R vector is equal to Vft plus R dash vector. Or I can write R dash vector is equals to R vector minus Vft. Now this transformation equation will help me. If I know R dash, I can find out R. And this equation will help me to find out R dash if I know R. So these two equations, 1A and 1B, they constitute first Galilean transformation equation. And if I differentiate these equations with time, that means I do this, dr vector over dt, since Vf is constant and differentiating will yield only Vf plus dr dash over dt, which means the velocity of the body in S frame is equals to velocity of the frame itself plus the velocity of the particle as observed in the S dash frame, or V dash vector is equals to V vector minus Vf vector. These are the transformation equation for velocity, that is equation 2A and 2B. On further differentiating this equation with time will yield the acceleration relation, and interestingly, since Vf is constant, so its time derivative is 0, we have acceleration observed in S frame is exactly equal to the acceleration as observed in the S dash frame. So this is the transformation equation for acceleration. Here it's very important to understand, when I say V, V is the velocity of this particle, where Vf is the velocity of the frame, A is the acceleration of the particle in S frame, A dash is the acceleration of the particle in S dash frame. So collectively, these three equations, they are known as Galilean transformation equation. There is a term associated with this that is called Galilean invariance. The meaning is, when I transform a physical quantity from S dash frame to S dash frame or vice versa, the value of the quantity remains same. Hence from these three equations I can make one statement: yes, the acceleration A of the particle is invariant in S, and in S dash frame the value remains the same. Moreover, the mass and time interval t are taken to be invariant in these inertial frames. If mass is multiplied with acceleration, I yield one equation, that is the equation for the force. Since A and A dash, they are same, so even the force remains invariant under the Galilean transformation equations. Since force is a basic physical quantity, looking at this we can make out whether the motion is a uniform motion or accelerated motion. And if that remains invariant, it means all the laws of motion are also invariant. That means you can apply the laws of motion in S frame, and the same set you can apply it in the S dash frame. All these three laws of motion, they are invariant. Apart from this, many other quantities which are invariant, we'll talk about this later, but there are some quantities which are not invariant. What are these quantities? Position. Position is invariant, velocity is invariant, and if you multiply by mass, that means the linear momentum. Linear momentum also is invariant. So there are few quantities which remains as it is when we shift from S frame to S dash frame, but for certain quantities we need the transformation equation. So these Gaussian transformation equation will help us to transform the quantity from one frame to another frame, but we must remember this, that these transformation equations are applicable only when the relative velocity between the inertial frame is very, very small as compared to the velocity of light. Thank you.